Lena, is Pete going to lift his microphone?
Yep.
What's he using?
Pete will have, yeah, Pete has his own.
Are you ready there, Sid?
Yep, ready to
Okay.
go.
Good morning, everyone. My name is Pete Guinoso. I'm from Blue Harmony. We're happy to be here supporting the Blue Ocean Dome and bringing in some wisdom from our elders. And today I'm really happy to share that Dr. Sid Thurston is here. It's my great honor to introduce him. He's a remarkable speaker. He's dedicated his career to both ocean advocacy and the burgeoning blue economy. And Sid was a leading expert at NOAA before retiring and a prominent figure in EarthX, where he worked tirelessly to bridge the gap between ecological sustainability and economic opportunity within the blue economy. As an ocean advocate, researcher, and thought leader, Sid's work has had a profound impact on advancing both ocean conservation and sustainable economic practices. Today, Sid will be presenting his talk titled, A Brave New Ocean to Power the Global Blue Economy. Sid's extensive experience from his work with NOAA to his leadership at EarthX placed him in a unique position to share invaluable insights on how we can move forward both ecologically and economically in this face of global challenges. And without further ado, please join me in welcoming Sid Thurston at the stage as he takes on his journey through the blue economy. Thank you, Sid.
Thank you very much, Pete. Minasama, ohayo gozaimasu. EarthX no Thurston de gozaimasu. Yoroshiku onegai shimasu. Good morning, ladies and gentlemen. I'm Dr. Sid Thurston from EarthX, where I'm the Global Science and Technology Director. It's a privilege to be here. I want to thank Soraya-san. I want to thank Pete for this amazing Blue Ocean Dome. And I want to thank you all for coming this morning to learn more about what science is telling us about climate change, what science is telling us about how climate change is impacting our precious blue planet, and how science is providing solutions. But before we do the science, I think we need to embrace the ocean in our heart. That's where it all starts. You don't protect something unless you love it. Think of your children, think of your family, think of your spouse. You need to embrace that dimension first. So let's get started. Every second we breathe, every time we take a breath, it comes from the ocean. Not the trees or the forest, but the kelp, the ocean kelp in the upper ocean. The ocean is not only vast, it is vital. It shapes our climate, it feeds billions of people around the earth, it absorbs carbon, and offers awe-inspiring beauty. Yet beneath the surface of the ocean, something is changing. And that's what I want to talk about today. So today I invite you to take a journey through the pulse of the ocean to see what it's telling us and how together we can steer its bright future together. The ocean is not just a system, it's a symphony. Imagine you're in a concert hall. That's what the ocean is. Its beauty is beyond measure. The shimmer you see here, the bioluminescent tides, the dance of dolphins in the surf, the swirling symmetry of coral reefs, seen from space. Yes, you can see coral reefs from space. These are not just aesthetic wonders. They stir something deeper in our hearts, a connection to mystery, to motion and meaning. And in that beauty, we find the reason to act, not out of fear, but out of reverence for the ocean. For millennia, the ocean has shaped human culture. It is woven into our stories, our songs, our identities. In Japan, we know the ocean is sacred. The Ama divers, women of the sea, harvested its gifts with respect and grace. Across the Pacific, Taiheiyo, Polynesian voyagers read stars and currents as if reading scripture. In the Arctic, the sea is a lifeline passed from elders to children. Protecting the ocean is not just ecological, it's cultural, it's in our heart. It's about preserving wisdom, resilience, and belonging. Again, you don't protect something unless you love it. You must love it. As an avid scuba diver, 40 years ago, the ocean inspired me to pursue my PhD in physical oceanography and contribute 28 years of my life to the United States National Oceanic and Atmospheric Administration. After my postdoc in Kurihama, Japan, and liaison at the Japan Marine Earth Science and Technology Center, I directed a NOAA office in Tokyo, Japan. My wife is Japanese, and we have 3 children. Our oldest daughter was born in Japan. So Japan is my second home, Japan is my love, and the ocean is my love as well. Climate change, we're hearing a lot about climate change today, refers to long-term shifts in temperature and weather patterns. Such shifts can be natural due to changes in the sun's activity or large volcanic eruptions. But since the 1800s, you can see here in the upper left panel, this is the surface of the Earth temperature changing since 1800. And of course, the reds and the dark browns are warmer temperatures. Human activities have been changing the temperature of the Earth, primarily due to burning of fossil fuels like coal, oil, and gas. Think of it this way, burning fossil fuels generates greenhouse gas, and that is like a blanket, taking a blanket wrapped around the Earth, trapping the sun's heat and raising temperatures. The main greenhouse gases are carbon dioxide and methane. These comes from driving cars, heating buildings. Today we are living in the hottest years in recorded history. This is not abstract data. These are observations and these are facts. We're seeing it in ice melting much more quickly in the Arctic, in Greenland, and the Antarctica. It's storms gaining strength. It's coral reefs bleaching in record time. The Arctic is melting faster than other parts of the planet. We often think about climate change as something in the future, but I think we're starting to realize that it's happening now. Ecosystems and people around the world are affected by the ongoing process of climate change. Climate change affects the environment in many different ways. We're experiencing hotter days. We're seeing temperatures in the 50 centigrade in India. We're seeing coral reefs bleaching, sea level rise, droughts, floods, hurricanes, typhoons. So these are happening today. But the good news is there is hope for the future. There is still time to lessen these impacts in the severity of climate change. We already know many of the problems and solutions, and scientists and researchers are coming up with new solutions every single day. Experts believe we can avoid the worst outcomes by reducing emissions to zero as quickly as possible. The ocean covers almost 3/4 of the Earth's surface. We are increasingly recognizing how much we rely on the ocean to support our human life, our economies, our culture, our environmental well-being. The oceans are our greatest buffer, so as the atmosphere warms up, the ocean is taking the heat. It's also taking the carbon dioxide. So scientists are measuring the impact of climate change on the global ocean. They're taking observations, and scientists are also predicting the future using models. So let's take a minute and see how we're observing the ocean and let's understand how we're predicting the ocean with models. You can't manage what you don't measure. You need to measure it, you need to see what's happening so you can manage. Ocean observing is essential for a better understanding of how society and all life on Earth is affected by climate change. The information gathered is invaluable to policymakers in individual nations. We are taking observations for storm surges and other warnings, marine heat waves, extreme waves, and other ocean phenomena. We're starting at the surface of the ocean, and we're going 4 kilometers to the bottom of the ocean, and we're taking observations through the entire water column. So let's take a look at one ocean observing program called Argo.
Scientists on research ships can sample the ocean only briefly, so they deploy automated devices for long-term ocean monitoring. This float is part of an international research program called Argo. It measures ocean conditions that drive events such as El Niños and climate change. Like a hot air balloon, it drifts along on slow-moving currents in the deep sea. The float dives by mechanically decreasing its volume in the water, and it descends to as far as 2 kilometers, more than a mile, to survey otherwise unmeasured underwater regions. Submerged for up to 10 days, the float can be programmed to stay at one depth or to move up and down to follow changing conditions. At preset intervals, it ascends by increasing its volume. Rising through many ocean layers, it records the ocean pressure, temperature, and salinity, collecting an up-to-date profile of evolving ocean conditions. At the surface, the float makes radio contact. Its new location reveals the features of underwater currents, and the data supply real-time measurements of subsurface ocean conditions, details unavailable without Argo. After a short period, the float is ready for another cycle, a process that can repeat for more than 5 years. With 3,000 floats in a global network, the Argo program will supply real-time ocean data for immediate use in research and operational forecasting of marine and climate conditions worldwide. Argo, observing the oceans in real time.
Okay, thank you very much. That's part one, and that's the ocean observations. And this is the program I started at the U.S. National Oceanic and Atmospheric Administration, NOAA, 30 years ago to measure the global ocean. And these are some of the tools that we use. You can see here, some stay on the surface, some go down to 4 kilometers, some measure waves. We measure the sea salinity, the ocean saltiness, the temperature of the ocean, and we also measure carbon in the ocean as well. So we are all connected by a global ocean, and this program takes over 1 million ocean observations every single day, and we transmit these data via satellite all around the world, so scientists have immediate access to these data at the comfort of their desk. In addition to observations, we are modeling the ocean. We want to see what we can expect from the ocean, and we have Yamagata Sensei is not with us today, but we have Behera-san. Behera-san is with us. He'll be presenting after me. And these are probably two of the most famous modelers in the world for ocean modeling, Behera-san and Yamagata Sensei. So let's take a minute just to see what they're working on as far as digital twins of the ocean.
We live on a blue planet which depends on the vitality of the ocean to support and sustain it. Not only does the ocean produce about half of the Earth's oxygen and helps mitigate climate change by uptaking human-generated carbon and excess heat, it is also an important source of food and livelihood for billions. But our ocean is in danger, as its health is dramatically declining. However, the ocean is also a great source of hope. By understanding and predicting what is happening, we can live more sustainably, adapting our activities to better preserve the ocean and its life-sustaining resources. This is why the development of the digital twin ocean is so important. Compiling terabytes of past, real-time and forecasted information from satellites and sea-based observations, the digital twin ocean combines improved AI with high-performance supercomputers to model the ocean's response to a range of future what-if scenarios in the short and long term. This virtual sea of data takes monitoring and forecasting to the next technological level, opening up a world of possibilities for many organizations and encouraging cooperation between scientists, researchers, businesses, policymakers, and the wider civil society. The Digital Twin Ocean is an accessible, open platform enabling users to create their own applications. Its data will help blue economy businesses with daily operations and plan future projects, from wind farms to more resilient coastal tourism, and make it easier for policymakers and organizations to adapt to an ever-changing ocean, from helping to mitigate the effects of pollution and fishing on marine life to the early warning of coastal flooding. Plus, researchers will be able to study the impact of climate change more closely, from ocean acidification to increases in water temperature. As a major step forward in operational oceanography, the Digital Twin Ocean plays an important part in protecting the ocean and creating a more sustainable future. Learn more about how the Digital Twin Ocean can benefit you and our planet.
Okay, thank you very much. We'll be hearing from Behera-san in just a few minutes. The ocean is feeling the heat. In other words, the ocean is taking the heat, if you will, from the beginning of industrialization until today. In fact, the oceans have absorbed 90% of the heat in the atmosphere has been absorbed into the ocean. Amazing statistic. This leads to rise in ocean temperatures. Here you can see on the graph the trajectory. As carbon dioxide rises, that's CO2, carbon dioxide, so do ocean temperatures, and so does the risk to the systems we rely on. As oceans absorb more carbon dioxide, they become more acidic. So the ocean water is more acidic, and it harms marine organisms, especially those with build shells or skeletons. Warmer oceans also cause the expansion of seawater, so this contributes to sea level rise. The warming ocean is a major warning sign of climate change with visible impacts like sea level rise, coral bleaching, and changes in ocean health. These changes are due to increased heat in the ocean, which increases the intensity of storms and rising sea levels. Coral bleaching, as you see in the left panel here, the left one is healthy coral, and after extreme exposure to warm temperatures, the coral is bleached white. Each of these changes is interconnected, and each one is accelerating. However, and this is an important point, each one is also within our power to influence. We have power to end this well. We are in control of this. It's not something that's beyond our control. So that's one of the main points. Marine life is moving. The ocean has begun to lose its rhythm. Currents are shifting. Ecosystems are moving. In some regions, we're seeing entire food chains migrating towards the poles. They need colder water. You know, if it's too hot for them, they'll either move towards the poles or they'll go deeper into cold water. And in fact, some species we've been monitoring are moving up to 70 kilometers per decade. They're migrating 70 kilometers. This shift in distribution can be visualized by this graph here. You can see the time scale. The blue is 2002, and the red is 2019. Some species moving northward or deeper into cooler waters are adapting to climate change, and the big question is, can we help them fast enough to adapt? We are also looking at changing coastlines. Over half the world's population lives within 100 kilometers of the ocean. This is a remarkable statistic. And as sea level rises, coastal displacement threatens millions of citizens. Yet communities are adapting. In Japan, the Netherlands, Maldives, just a few examples, we're seeing a rebirth of coastal planning that works with nature. In 2020, Japan passed its basic policy for coastal protection. Communities are implementing traditional practices such as planting trees along the coast to provide protection from storm surges, tsunamis, and other coastal hazards. In some cases, especially some of the small island developing states in the Pacific, plans are underway to actually relocate to higher ground. We are in danger of losing what makes the ocean such an important and special place to many of us who rely on it for livelihoods, food, recreation, and moments of wonder. The ocean doesn't need saving, it needs partnership. And again, we have to love something to protect it. We are not separate from the sea, we are part of its story, and now we are writing the next chapter. We are still writing the next chapter. Across the world, people are restoring reefs by hand, planting mangroves, sustainable fisheries, growing sustainable blue economies. The ocean has always been generous. Now is the time to give back, not just for its survival, but for our own survival. It's for our survival as well. Positive change is happening, so I'll go through just a few quick examples of hope and optimism, because people are getting it, they're making changes. In 2023, Parliament passed the High Seas Treaty, protecting marine life beyond national borders. Across the globe, young voices are rising to defend the ocean, demanding climate justice and ocean equality. The tide is turning. This is our chance to protect it. Marine protected areas, or MPAs, in the area they cover has increased significantly in 20 years. There used to be 500 MPAs, and now there are 16,000. 25 million square kilometers are protected from human involvement. 7% of the ocean surface is now MPAs. Sustainable shipping, this is also known as green shipping, focuses on minimizing the environmental impact of cargo transportation. This includes adopting practices like reducing carbon emissions, optimizing fuel efficiency, and using cleaner technologies. Companies that prioritize sustainability can build a positive brand image and attract environmentally conscious customers. So this is one big example of turning the tide to sustain the oceans, sustainable carbon and shipping. Of course, we all know about plastics. We'll be hearing about plastics the rest of the afternoon. Sustainable fisheries is another one. Sustainable fisheries provide a vital source of protein for millions of people worldwide. Sustainable fisheries support fishing communities, related industries creating jobs and contributing to local communities. Sustainable fisheries use science for fish quota, stock assessments, and their habitats continue to provide benefits for the future generations. So in conclusion, The ocean can, and it will, recover. We just have to think about it more wisely. It will recover with our help. The ocean is not gone. It's still full of life, of power, of possibility. It's in our hands. It has always healed in the past when we let it. Every minute since I wrote this slide, it's increased to 2 truckloads. 2 truckloads of plastic every minute enters the ocean. From the remote Arctic to the deepest trench, plastic is everywhere, and we'll be hearing from Mary in just a little while about that. Some of it breaks into microplastics, now found in the fish we eat and the water we drink. Some drifts into vast gyres, floating islands of waste, while some sinks silently choking marine life. Again, here's another powerful truth. Marine plastics is one impact we can reverse. I encourage you to please take a picture of this QR code right here and make a pledge. Make a pledge. You can sign this pledge that I refuse to use single-use plastic. It's the biggest thing you can do today to help the oceans, is taking this pledge. So I'll leave it up here for a few more seconds. It's a powerful statement that enough is enough. This is in my control. I can make this decision to save the ocean, and I choose to make a positive decision today to save the ocean because I love the ocean. So let us leave this magnificent, spectacular blue ocean dome with wisdom. Hopefully we've learned a little bit more about the science of climate change. We've learned a little bit more about the science of how climate change in the atmosphere is impacting the ocean. And now we are empowered. We feel more empowered. We are in control. So let's leave this amazing blue ocean dome with courage and care, and let's give the ocean a chance. Let's just think wisely about this, and it will give us the future. So today at Expo 2025, we stand at a threshold, not just to observe and talk about it and then go home and make poor decisions. We stand at a threshold to choose wisely. What kind of ocean legacy do we want to leave our precious children? Again, you don't protect something unless you love it. So with that, I'll conclude my remarks. I'm happy to take any questions. I see a couple more minutes here, and I'll just say domo arigato gozaimashita. Thank you very much. Please, Soraya-san. Onegai. Thank you. Yes, please. Yes, Soraya-san. It's an amazing organization. It's a global organization, not for profit. It is dedicated to bringing people together all around the world to come up with solutions to solving the global environmental challenges of the planet. That's basically what we do. We don't have an agenda. We don't have a bias. We bring people from all walks of life together to come up and talk wisely and fairly and sincerely about solutions to solve the global environmental challenges. That's EarthX. We've been in existence for 15 years, and it's based in Dallas, Texas. Thank you.
Okay, thank you so much, Dr. Thurston. Appreciate you being here.
Thank you very much, Pete. Yeah.
Okay. Yep, okay. And good morning, everybody. I'd like to invite you to give a warm welcome to Dr. Behera, a leading expert in ocean science and climate action whose work at the intersection of technology and environmental preservation is shaping the future of our planet. Dr. Behera is well known for his groundbreaking work in climate and ocean science using cutting-edge technologies like digital twins and artificial intelligence to transform the way we understand, predict, and respond to climate extremes. As the world faces more frequent and intense climate events such as floods, droughts, heat waves, and wildfires, Dr. Behera is at the forefront of harnessing advanced modeling systems to improve our ability to tackle these challenges head-on. Please join me in welcoming Dr. Swadhin Behera as he shares his vision of how we can build a more resilient, sustainable future through the power of digital technology and climate action. Thank you, Dr. Behera. Yeah, you're welcome.
Maybe I'll stand here closer to you. Thank you, Peterson, for your nice, kind introduction. I thank Mr. Saraya and you for this nice opportunity. It's an honor and pleasure to be here. As we hear in Dr. Thurston's presentation, he made a presentation about what we have now, what we are heading into, and what kind of observations we have to monitor what is happening now. So I will do the next part. We have the observations, we know what is happening. How do we know what will happen in the future? Especially, we know that many extreme events are happening now. You can see that very recently we have this flood in Texas. 100 people, more than 100 people died, many are missing. We know that similar floods already occurred in Spain, in China, and also in Siberia a few days ago. It was heavy rain, and suddenly the JR station in Siberia got flooded. And that can happen to any part of the world, any cities in the world. And we believe these kind of extremes are increasing in numbers and also getting more intense. We have heavy flood within few minutes, like in 20 minutes we have a lot of rain, and then the rainwater cannot be drained out, so we have flash floods. And also the temperature, global temperature is rising. Every summer is getting hotter. And as you know, particularly this year, the rainy season in Japan got shortened. We didn't get enough rain this year. Most part of Japan didn't get enough rainy days in this rainy season. And it's already hot. Like many areas are experiencing 35 degrees. And we are lucky this morning, it was not so hot because of the rain. But as the day progresses, we'll have a hot day today. And as rightly said by the UN Secretary General, we are entering into an era of global boiling from global warming. The time has gone when we are talking about the global warming, we are talking about the global boiling. As you had, Dr. Thurston mentioned that some parts of India already experiencing more than 50 degrees centigrade in summertime. And that can also happen in Africa and other regions. And we know that Europe is facing a heat wave. Last few weeks, Europe had a heat wave. I was in Paris. Few days ago, it was very cool, very nice, but suddenly it became very hot. And you know that many of the systems in Europe are not built for hot days. Not good ventilation, not good air conditioning. So when heat waves hit Europe, it really gets really bad. Spain was experiencing more than 40 degrees for some days. So those kind of extremes we are going to see more and more, and they are going to be more intense. Then the question is, can we predict them? Is there a way we can say, at least a month ahead or 2 months ahead, that, okay, next summer is going to be very hot for Japan, or next summer is going to be very rainy for India? And can you do that for all regions in the globe? The solution to that lies in the fact that most of these extreme events, drought, flood, heat waves, they're some way or other related to climate phenomena. These are kind of ocean-atmosphere coupled systems. They evolve once in a few years, not every year, once in a few years, like El Nino. It happens over the eastern part of West Pacific. And when the temperature is warmer in the eastern part of the Pacific, that affects the weather and climate all over the globe. So some parts becomes very dry, as you can see for El Nino 2006, 15, and El Nino Modoki 2002, 4, 9, 12, 14, we had heat waves in many parts of the world. And also La Nina, the other side of the El Nino, can also affect many parts of the world. When you have a La Nina, many regions experience heavy floods. And we also have similar phenomena in the Indian Ocean called the Indian Ocean Dipole. So when Indian Ocean Dipole happens, it affects the Indian monsoon, Asian monsoon, and also the East African rain, Australian rain, affecting not only daily lives, but also agriculture and other things, indirectly affecting the economy. And on top of that, we have the global warming. So once we have a global warming, it has a direct impact on those extreme events. So those are getting more intense and more frequent. And the global warming also modulating these climate phenomena. So we see more El Ninos in some decade, more dipoles in some decade. And because of them, we can experience more heat waves, rain, or droughts in particular part of the globe, depending on their sphere of influence. Now, once we know that they are related to climate phenomena like El Nino or the Indian Ocean Dipole, these are coupled systems. Ocean atmosphere interact and produce those systems. And because ocean atmosphere interact, we know the processes, how they interact. So we can predict them once we have those systems in a computer. So virtually we create ocean and atmosphere and land and the ice and the rivers in the ocean to produce kind of global climate model inside the model to simulate the climate phenomena and also predict them for the future. And the first model was started by Suki Manabe. Manabe sensei, he was in Princeton University, and he started a toy model by coupling Atlantic Ocean to the atmosphere. Why Atlantic Ocean was important for him? Because Atlantic Ocean has a meridional ocean circulation that kind of regulates the heat. And many people talk about this circulation getting shut down, and we saw many movies that shows how the sea ice melting in the Greenland region can affect this meridional overturning and then shut down the global cooling, and we will enter into either a very warm age or a ice age, depending on what is the scenario we have based on the shutting down of that meridional overturning. So Manabe Sensei was not interested in those things. He was interested more into what will happen to our climate in the future. And we cannot know the future of the climate unless we have this kind of model, which is kind of coupling ocean and atmosphere in a virtual system. And he tried this toy model in Princeton University in 1960s, and he was successful. And that legacy continued until now. So he tried a very coarse, like 500-kilometer model, 500-kilometer by 500-kilometer model. Now we have a global model with 10-kilometer resolution. So we have increased the resolution. We have increased the processes inside those models. And that's why these models are able to provide us very accurate ocean currents, temperature, salinity, the atmospheric rainfall, and the atmospheric teleconnections coming from those climate phenomena. In that way, we are able to predict very detailed climate processes now, And based on that, we will be able to tell, okay, these are the regions which are going to experience extreme events in the coming seasons. Whether we'll get heat waves or a flood or a drought, we can predict because we have the models which are able to provide details at this stage because of their high resolution and resolving many, many processes. And we are also tying not only one single model, but we have many models at different operational centers. And then we take, because each model has its own bias, the way it is resolving the processes. Some models do better, some models doesn't do better for one process, but do better for the other process. So what we do is we take all the models available to us and make an ensemble average, ensemble model average. So we have many models, take the results from all of those models, make an average, then we have more confidence on the scale of those models. And that's how we are able to predict now extreme events besides those climate phenomena. I'll give you one example what we are doing at Jamstec, where I am for the last 27 years. We developed a coupled ocean atmosphere model, Taiki Kayo Ketsugo model, and that model is about the atmosphere model and the ocean model coming from the European Center, and we are coupling that on the Earth simulator. Each component is developed separately in different center in Europe. This is a Europe and Japan collaborative development using the Earth simulator that we have in Jamstec. And the atmosphere model, we started with a resolution of 100 kilometer. The ocean model also was 100 kilometer. The present model is, atmosphere model is like 50 kilometers, and the ocean model is 25 kilometer. Our aim is to go to 10 kilometers, but for that we need faster computer and better archive space to keep all the data. But this model is already doing very well to predict the phenomena like El Nino. On the left, on your left, the diagram below is showing you the prediction of the El Nino index. We picked up the El Nino area and make an index and try to predict them using these global models. And as you can see, the red line on top is the model predictions coming from Syntex, the model we are developing at Jamstec. You can see up to 6 months ahead, the model prediction and observation correlation is 0.9. On the left, the scale is correlation scale. So up to 6 months ahead, the model and the observation correlation is 0.9, which means the model is almost telling us 100% when we'll have an El Nino, when we'll have a La Nina. And this is the top model in the world. There are several models coming up now, and we're extending the lead time of the forecast from 6 months to 2 years ahead. So 2 years ahead, we have confidence now to tell whether we'll have an El Nino or a La Nina. We are also doing the same thing for the Indian Ocean. So Indian Ocean dipole are also predicted well, at least 1 season ahead. And we continuously develop this model, improve the predictions. We know that sometimes model has the bias, sometimes it fails to predict, sometimes it fails to predict the initiation of the El Nino or the termination of the El Nino. And that's why we are kind of improving the model. There are several ways to improve the model. One way is to take all the subsurface data. Below the surface, as you remember, Dr. Thurston showed you the Argo floats, which are taking the observation from the surface to 4 kilometers below the surface. And those data we put into the model at the initial stage. So the model knows what is the state of the sea, not at the surface, but also at the subsurface, which are important because they are providing the necessary heat to the atmospheric systems. So we are putting all those observational data into the model, and that is improving the predictions, especially away from the tropics. In the subtropical regions and extratropical regions, the model predictions have improved by including those ocean subsurface data. We are also increasing the number of ensemble members. Ensemble members are kind of different realities produced at the same time. So we know that atmosphere has signal and a noise. We want to distinguish between signal and noise. We want to catch the signal. If you take the noise, we'll produce the noise, and the prediction will be wrong. We need to pick up the signal, but we don't know where is that signal, at which time, and in which space. So we do many ensemble predictions, not one member, but many members, by taking different observations at different time in the past, hoping that one of those members might be capturing the signal. And then put all those ensemble members together, make either an ensemble average, and we found that that's better than predicting by using just one member. And by increasing the number of ensembles, we have now like 126 members. Some of the models that are predicting typhoon, hurricanes, are using AI to emulate 3,000 members. It's kind of impossible at this stage to do that using these kind of big global models. But using AI, you can produce like 3,000 ensemble members. That gives us more confidence, more probability to predict the events correctly. This is the prediction for this season, July to September. As you can see, the plot here in the bottom left, most part of the globe will be warmer than normal. So it's going to be a hot summer, especially for Japan and Europe, and also some parts of the US. The red and very red colors are actually going to be very hot. That's what we predict for the next season, from July to September. Some parts like India will also be getting a lot of monsoon rains. The green color on the right shows you rainfall. So many parts of India and some parts of South America will get a lot of rain. We also expect probably East Africa will get a lot of rain this time because there is a possibility we'll have a positive Indian Ocean dipole. So one issue is these are the global plots. The other thing is we see are the El Nino and the Indian Ocean dipole index predictions on top. Usually, as I said, the climate phenomena like El Nino and Indian Ocean dipole are linked to extreme events, rainfall or drought or heat waves. When you have El Nino, we know which regions are going to be experiencing drought, and which regions are getting floods. We know that. But when we don't have El Nino, it becomes very difficult. That is the signal we have. So if you lose the signal, it gets really difficult to predict what will be the extreme events, which regions will experience floods, which regions experience the drought. And for that, we know models have limitations. For that, we are now turning to AI. We know AI can pick up the signals from the past data and tell us what will happen in the future. AI is helping us making better forecast by improving the data assimilation we are doing at the beginning of the forecast, also by improving the results when we have how to make the ensemble average, just arithmetic average, just the mean, or just pick up the best models out of those ensemble members and improve the mean of the predictions. And also provide a better user interface based on the past information and based on the stakeholders' interest, what they want, what the demand they have. And I'll give you a few examples here. This is the example where we are selecting the ensemble members. We are not taking all the ensemble members and making an average. We are selecting ensemble members. And by selecting ensemble members, as you can see, on the extreme right, you have the selected members, and the yellow means the skills of predictions are better than the one on the left, which are very blue. So many regions, especially Kanto region, the Hokkaido region, the temperature predictions are better when we select ensemble members using AI. We are not only using AI to improve the dynamical climate predictions, but also use the AI to improve the climate predictions by themselves. So this is one of the examples where we are using the deep learning technique called the convolutional neural network, CNN. And this is a very fantastic system to predict the future El Nino state by just using observational data. It's not using any model. It's just taking all the available observation in the past and then predicting what will happen 3 years ahead, 36 months ahead. So the model scale is quite good up to 2 years ahead, where the correlation between observation and the model is above 0.4, 0.5. But we are trying to improve on that and also try to make multi-year prediction using AI. Now, once we have good predictions, then we apply them for various societal needs. One of them is health, infectious disease. We try to use those climate predictions to predict malaria outbreaks in Southern Africa. And we have been successful doing that for the Limpopo province in South Africa, and we are expanding that to Zimbabwe, Botswana, and Mozambique, where the number of cases are very high. We also do the crop yield forecast by using both climate and crop models, and also AI. And the skill for predicting like maize, rice, wheat, and soybean, quite good 3 months ahead. So 3 months ahead, you can provide a crop yield forecast. Okay, these are the regions where you will have more maize. These are the regions where you will have more rice and more wheat. It's helpful both for the farmers and also the policymakers who are kind of managing the crops in their region, like the food and for the food security. And we are also developing the digital interface, which will provide the information to everybody, all users, all general public can go into this JAMSEC website. This is a kind of 4-dimensional virtual earth we are creating, the digital twin of the earth. And anybody can go click in to get the results for their region. And eventually at the moment it's 2-dimensional, eventually we'll make it 4-dimensional. And also we'll put AI into that, so users can ask like ChatGPT, what will be the scenario for me for agriculture or for health practice or water management or energy management. And create a kind of digital interface for various societal applications. And this is my summary. So evolving seasonal climate forecast system now deliver actionable information to support decision-making in diverse societal sectors. The role of ocean is very clear. We need to understand the processes through the ocean and improve our predictions through the ocean. Smart interactive interfaces will be useful for multidisciplinary approaches, not only for climate risk assessment, but various other assessments for our society. And digital twins is the future for us using the AI and machine learning. I'll stop there and take any questions. Yes, Peterson, yes.
Making these predictions more and more difficult, the government policies and stuff like that. Have you seen that, or what do you think? Like, is it like after 3 years, it's good data, maybe after that it's harder?
So we have 2 target periods for predictions. One is multi-year, like 1 year or 2 years ahead. That's where we have the skill now. The other one is what will happen 50 years ahead, 60 years ahead, 100 years ahead. That is the most difficult one to say now. We don't say prediction, we say projections. We are projecting what will happen. And projection will depend on various things. As you said, the government policies to reduce the greenhouse gases. At the moment, we are having several scenarios. Okay, if the business goes as usual, then the future greenhouse scenario will be like this, and those greenhouse gases are included in the model to predict what will happen in the future. The most important thing we are missing at this stage, I'll show you that in the seaside chart just now. The oceans are absorbing a lot of heat. They are able to absorb this heat because there is a ventilation system in the ocean. The subsurface is cold, the surface is hot, and we have this ventilation system to ventilate the warm temperature from the surface and bring the cold temperature to the top. And that ventilation is working perfectly now. That's why we are able to absorb a lot of the heat that we are producing now. But we don't know how the ocean will behave in the future. If this ventilation system will persist, or there will be a break in that, or we might have a weaker ventilation system. Those scenarios are not clear to us. And models are not able to capture them well. We don't have confidence on the models if they are able to capture those scenarios in the future. This is one of the scenarios. The other scenario is how the clouds will form, whether the temperature rise will absorb more moisture in the atmosphere, or those moisture will be converted into rainfall. So those things we don't know yet. So those sensitivity of our Earth is unclear to us. And that makes the future projections very uncertain at this time. So that's why we don't try to project or don't try to give a lot of confidence on the projections 50 to 100 years ahead. What we are trying to see is what will happen in 1 decade ahead, 10 years ahead, 20 years ahead, where we have more confidence on the processes we know. Thank you.
Okay, thank you so much, Dr. Behera. Please give a little applause for Dr. Behera and his beautiful talk. We're lucky that we have both Dr. Behera and Dr. Thurston here to share, and they'll be providing an oceanside chat, not a fireside chat, as some of you may know, an oceanside chat. It's very exciting. Is that not funny? Is this thing on? That was it. Yeah. Thank you. Thank you, Dr. Behera. I appreciate that. Okay. Okay, just a little brief reminder. Some of you are newer to this area, this Wisdom Dome Sea. Dr. Thurston was a leading expert at NOAA, and he's a prominent figure in EarthX. And as you just heard, Dr. Behera is a preeminent scientist in the field of global ocean and climate research. And we're really happy to have them here to share. And just a kind of little background around this, we thought it would be nice to bring in both a Japanese expert as well as a Japan expert, as well as an expert from the US to share and kind of combine forces to share their wisdom with you. So we're really happy to have them here. Give a little warm applause to the team up there. Thank you.
Okay, thank you, Pete. Thank you for inviting us for this oceanside chat. Behera-san and I have been working together for well over 2 decades, so we know each other very well, and we're very excited to have this oceanside conversation. So let's go ahead and get started. You heard our presentations, and now we're going to unpack a little bit more detail of what we presented briefly earlier this morning. So my first question, Swadhin, is how important is the ocean to our lives? Let's unpack this a little bit more. Thank you.
Thank you, Dr. Thurston. Thank you, Dr. Thurston, and it's a pleasure to be in this Oceanside chat. As we know, the oceans play a very important role in our life. A few minutes ago, I just showed you how oceans are important for the ocean atmosphere coupling the coupled phenomena, and they are linked to extreme events. Ocean also is kind of provider of our food and livelihood. In 2022, we reached a peak of 223 million tons of fishery captures, and 70% of that was from Asia. So we are the largest producer, and also we are the largest consumer. And that's why the ocean is very important for us, not only for the food, but also for the livelihoods for many people. And as you can see in this diagram, we have 9% from Europe, 9% from Caribbean, 7% from Africa, 3% from Northern America, and 1% from Oceania, the fish capture we are having from these regions. And the consumption could be much higher in some of the regions compared to their production. So that sense, it's very important for the global economy to have a healthy ocean with healthy return with this kind of good fish catch. And also an estimated 50 to 80% of the oxygen produced by the ocean. So the oxygen we are having, one day I was reading a news in which they said the Amazon forests are dying and maybe getting destroyed. And at some point, we don't have the Amazon forest, and that will cause like 20% reduction in oxygen. So many people will die because of the reduction of the oxygen. So you can see that 50 to 80% of oxygen are coming from the ocean. So in that sense, ocean is very important for us. And then not only ocean supports livelihood and the food through the marine products, but also because of the rainfall that we get, most of that is coming from the ocean as moisture, water vapor. So the water vapor coming from the ocean produces the rainfall over land, and that helps us in agriculture and farming. And 1.5 billion people are dependent on those rain-fed farming. So rain is coming from the ocean, and the farming is because of the oceans, and 1.5 billion people are dependent on that. For example, if there is a problem in monsoon, many parts of India will suffer from drought. There is a problem in the rainfall over Australia. The wheat production will be reduced, and that will not affect only Australia, but global, all over the globe. So we know that this kind of interaction between ocean and atmosphere leading to the rainfall is helping us in our agriculture, and we need them to be stable. If they are not stable, we'll have problem in the future. The oceans also regulate the CO2. Dr. Thurston, you saw that because of the CO2 fluxes into the ocean, the acidity is rising and the pH balance is destroyed, and that is going to affect the coral reefs, the carbon cells of many sailfish. And that is a big issue, because about 25% of the excess CO2 we produce is actually absorbed by the ocean. And we know that the absorption at this moment might be higher or lower depending on the marine ecosystem, because most of the carbon dioxides are absorbed by phytoplanktons and the ecosystem in the ocean. So if the ecosystem is increasing in the global warming scenario, then we'll have more flux of CO2. And if it is reducing, then we'll have less flux of CO2. In both scenarios, we are in trouble. Either reduction in marine products or increasing temperature because of higher CO2 in the atmosphere.
Excellent. Thank you very much, Behera-san. So my question was, how important is the ocean to our lives? And you really answered it very, very well. Thank you very much, Swadhin. I think we forgot one reason the ocean is important to our lives. We love the ocean. We love going scuba diving. We love going swimming. We love going to the beach with our family. We love watching the ocean. We love meditating with the ocean. And I think that's another big reason why the ocean is important to our lives. But thank you very much, Swadhin. So we know the value of the ocean, but we get a sense that something's changing in the ocean. So how threatened is the ocean by human causes, what we call anthropogenic? Anthropology is study of humans, so anthropogenic means human-induced changes to the ocean by burning fossil fuels is one example, CO2, methane. So how threatened is the ocean due to human impacts? Thank you.
Thank you, Sidson. So I picked up this slide from your presentation. As you can see here on the left, the temperature over the globe is rising. It's like 1.2 degrees centigrade compared to what it was in 1880. In the last 130, 40 years, the temperature has gone up by 1.2 degrees centigrade globally, if you take a global average. But if you look at different regions, like some part of Africa, Western Africa, the temperature is much, much higher, 3 to 4 degrees centigrade higher. And some part of Europe, some part of America, both North and South America, the maritime continent, and some part of deserts, the temperature are much higher than the global average. And we expect those temperatures to continuously rise in the coming future if you don't take any action at this point. So people talk about the tipping points. There are tipping points. I'll come back again and again to this tipping point discussion. So there is a tipping point for the global temperature. So we don't know what it is at this moment. But if we are reaching a state where the tipping point, we have already passed the tipping point, then it is impossible for us to go back to the past stage, irrespective of what we do in the future. So we should avoid those tipping points. At this moment, we are still modeling and trying to understand what is the tipping point for global temperature, how long the ocean can sustain the excess heat transferred from the atmosphere to the ocean. Can it will be sustained, as we were discussing before? And if there is a tipping point, it cannot be sustained. And once that happens, there is no coming back. We should avoid at any cost reaching that tipping point. The same thing also for the ice melting. We know that we are already, I think, at the tipping point or past the tipping point for the Arctic sea ice. Much of the sea ice have already melted, and that is affecting the climate in Northern Hemisphere. And we hope it is just restricted to the Northern Hemisphere, but we don't know. Maybe there will be consequences coming from that, indirect consequences coming out of that melting of ice. It's not only increasing the global temperature, but also helping rising of sea level. Many of the global cities are dependent on the coastal systems. They are on the coast. New York, Tokyo, Mumbai, London, they are all coastal cities. And they are mega cities because they are able to produce things and transport things from one city to another city using the marine shipments and marine cargo routes. And that's why they are based in the sea, on the sea. But the problem is, as the sea level will rise, these mega cities and the economic centers will be affected. And we don't know whether the sea level rise is going to be continuous or decade-wise. If it is continuous and abrupt, then we will have a big issue for all those mega cities. Like the Mumbai city, there is a big population. Even Tokyo has a big population. And a lot of economic activities dependent on that population. So the sea level rise is going to be a big issue for all those mega cities. The ocean also absorbs, as we saw in your slides and in my slide, oceans are absorbing heat. 90% of the heat that was produced in last 100, 120 years are absorbed by the ocean. And one of our colleagues from NOAA, Levitas, he has retired now, and he wrote a paper in 2012 by comparing the data from 1955 to 2010, and he said that if the heat which was absorbed by the ocean is not absorbed by the ocean, the atmosphere will be heated by 36 degrees centigrade. Nothing will survive. If we have no oceans or the oceans are not absorbing the necessary heat, we cannot survive. Just in that 50 years, 60 years, the temperature would have gone up like 36 degrees centigrade. For example, if you say that, okay, the ocean atmosphere are working well, and ocean can still absorb the heat, but not the 90%, but only 40%, then we still have like 18 to 20 degrees centigrade rise. That is huge. And we should think about that. And we should think whether we are in the tipping point for that. Thank you.
So I'm trying to understand that statistic, Dr. Behera. If the ocean does not absorb the heat, the atmosphere would be 36 centigrade or plus additional 36. Plus 36.
Yeah. In addition to what we have,
In
plus
addition
36
to
degrees
today,
centigrade.
it's okay.
Yeah.
So it'd be additional 36.
So like 80 degrees for some parts of the world.
Thank you.
80 degrees centigrade, not Fahrenheit.
Centigrade. So we've been looking at how important the ocean is to our lives, and we're getting a sense of how humans are changing the ocean. But what are some of the consequences to this? What are some of the impacts that we are seeing and touching and feeling, not just reading about, but actually experiencing in our lives today? That what are some of these consequences that we can definitely say, yeah, that's real. That's not just theory. It's not just a model. It's not predicted or projected. I feel it every day. I'm experiencing this. So what do you think about the consequences that we're experiencing?
Thank you. I picked up again your slide from your presentation. So you can see that extreme events are rising. You rightly pointed out that some parts of India getting plus 50 degree plus centigrade in summertime. And the hurricanes are getting stronger, the typhoons are getting stronger. We have persistent droughts happening for several years continuously. We have the forest fire, the Los Angeles was devastated last year. And then we have floods. We have seen the floods in Texas a few days ago. We saw that flood in Sibiu a few days ago, as I said in my talk. And that's happening in many places of the globe. The heat waves are rising, heat waves are getting intense, and there is no respite. We don't see any respite unless we try to change the climate, returning back to the previous stage. And we see that continuously in many other things. In marine lives, I have again picked up this slide from your talk. The coral bleaching. We see a lot of coral bleaching nowadays because of rising temperature in the ocean. The issue is we used to have coral bleaching. When you have an El Nino, we used to have coral bleaching in Pacific, in the Indian Ocean, in the Great Barrier Reef, everywhere. We used to have that. But that only used to last for a few seasons. But with global warming, that few seasons will be extended to few years. Maybe never will come back to normal state. Because these corals take a lot of time to recover. It takes only a few seasons to destroy them, but recovery takes much longer. And with our intervention, we might improve that, but then the global warming is destroying, and we might have more coral bleaching, and we may lose some of these corals in many parts of the global oceans. And as you also pointed out, the sea level are rising, and that is a threat for many of our cities, and some of the islands in the Pacific are threatened. Some of the islands are already seeing very high sea level rise in recent years, and we believe some of these islands will vanish if this continues as we see now. Also, we see marine heat waves. They are getting more intense and more widespread in many parts of the global ocean. And we believe the marine heat waves will affect the ecosystem and the fish catch, because those are happening in the regions where you have the highest number of fish catch. And marine heat waves will reduce the fish production. Food security will be an issue for many parts of the world because the marine foods provide a cheap source of protein. And once we lose that, malnutrition will be a global phenomenon. And we also see many hazards because of storm surges, because of intense hurricanes, typhoon, and storm surge. We see coastal hazards. And also harmful bacteria are rising now because of higher temperature and pollution, marine pollution. We see red tides, cyanobacteria, and many harmful bacteria. And that is affecting both marine lives and also the quality of the water. As Sidson was mentioning, the oceans are also a good place for recreation. We go there for diving, we go for swimming, or just walking on the beach. Rejuvenates us, and that we are going to miss if the quality of water goes down because of global warming and the pollution. And we have many harmful bacteria, so swimming will be difficult, and also it will be harmful for marine lives, affecting again the food production coming from the marine sources. We also have the rogue waves, also called freak waves. These are waves 3 to 4 times higher than standard waves. And once we have the rogue wave on the seaplanes, that will destroy the shipping lanes, that will break the ships and destroy the cargo. So we are seeing more intense rogue waves and more frequent rogue waves, which are more difficult to predict now because rogue waves are random. They are kind of noise. There is no signal for them. They are noise. They are most difficult to predict. And we know that climate change are making them more intense and more frequent. So one way is to reduce them is to returning to our normal state by reducing the global greenhouse gases and global warming, I think.
Thank you very much, Behera-san. I've been following discussions with great interest on extreme events, such as hurricanes or typhoons. There's serious discussion underway now. For many, many years, hurricanes have been rated from 1 to 5 on the Saffir-Simpson scale, 1 to 5, 5 being most intense, and number 1 being a weak hurricane. There's serious discussion, scientific discussion underway now about a Category 6 hurricane that may be employed using Category 6 in the near future. The scale is based on maximum wind speed, it's based on maximum precipitation, and it's also based on damage to buildings and structures. And for many, many years, a Category 5 was the most we would ever experience. As I said, there is discussion now. Scientists are looking at Category 6.
Also, the winds are getting very strong, not only for the hurricanes and typhoon, but in general, we get gusty winds sometimes. And gusty winds are most difficult to predict unless they are linked with some weather or climate phenomena. Like if we have a typhoon, a tornado, or a mesoscale event predicted by our models, it's easier for us to predict gusty winds. But sometimes they just happen randomly. And those are increasing nowadays, not only affecting the coastal regions, but also affecting the flight paths. Yeah, some of the flights are affected by this gusty wind turbulence. And that is increasing nowadays and kind of causing a lot of concern for even flight paths.
Before I retired from NOAA, I contributed to a program to improve the intensity forecasting of hurricanes. We knew where the hurricanes were going with models fairly well, but intensity was hard to predict. And one of the reasons was the hurricane would be traveling along over the water and hit very warm water. And of course, that's the fuel for hurricanes is warm water. So we started a program. We would fly in front of the hurricanes and deploy instruments directly into the storm track to measure the upper ocean heat content of the oceans. And that has helped improve the hurricane intensity forecasting. It's all about the energy in the ocean. Should we continue? Would you like us to take a break? It's totally up to you.
I have a question.
Please.
Yes. I was curious, did you have a story that you would like to share of some possible hope? Because you've shared a lot of dire consequences here, and I'm kind of curious as to what you can provide with our audience that might support them to be inspired to do something about this.
There are tremendous reasons for optimism. The next generation is just taking it on. They're very passionate. They know how to work the system, and they're making really big roads towards a solution. Science has many solutions, but it's all about policy and implementing those good solutions. As I presented, Pete, in my presentation, some of the positive actions are shipping. Shipping is using more eco-friendly fuel. They're reducing their CO2 emissions. They're reducing fuel consumption. And that's a big part of the impact to the ocean. These huge 300-meter cargo ships, oil tankers, plying the global oceans The IMO is the part of the United Nations International Maritime Organization is making progress with their actions and their recommendations and their mandates to reduce fuel consumption, use cleaner fuel, reduce CO2 emissions. The models are getting better, and that is allowing ships to operate more efficiently at sea. If there's a current, for example, they can avoid the opposing current. They can use less fuel. They don't have to push so hard against the current. Fisheries is becoming more sustainable as well. There's a lot of activity there. Clean sourcing, responsible sourcing of fisheries. A lot of the big food companies are looking at more responsible fishing, working with small island developing states, looking at how they can fish more successfully and more sustainably. I know a lot of the big companies in America, the Walmarts, the big food companies, they are insisting on clean catches, no bycatch, reducing bycatch, just getting the main catch. So fisheries, shipping, ecotourism is another area that's emerging. I'm very excited about ecotourism, whereby you don't have to deplete fish stock. You're seeing fish as a tourism attraction, and the economies are thriving on ecotourism, coral reefs, fish. The world is changing, Pete. The world is getting it. They're starting to understand that we only have one blue planet, and if we want to sustain it and preserve it and love it for the next generation, we can't continue the way we've been going with the ocean. And with technology and science and AI, I am extremely optimistic and extremely hopeful, and with policy changes as well. I showed the map of the marine protected areas. These are huge, huge areas of the open ocean whereby, we're not going to allow huge ocean fishing to go in there and just ravage those MPAs. They're protected. The P stands for protected, marine protected areas. There are strict rules. And 30 years ago, there were about 500 MPAs. And now there are 16,000 MPAs around the world. And that's a good sign for optimism and hope, I think. And you could go on, but science has solutions. Science is always producing new solutions and discovering new ways to work with the ocean more sustainably. You may have heard about deep sea mining is another big area of concern. And there are different ways of doing it. Some are ravage the seabeds, but there are more increasingly clean ways of deep sea mining. That's just one example. But there's a lot happening, Pete. A lot of good things are happening. Thank you.
Good. Can I add in? And of course, if anybody wants to ask any questions, feel free. But the other, just a follow-up question to that. I heard you share a lot of things that are happening kind of outside necessarily of our purview, as individuals' purview. Is there something that you would share with the audience, both you and Dr. Behera, about what somebody can do individually on a daily life? Is it, what would you suggest for someone who's listening and says, I want to get involved, but I don't necessarily, I don't own a shipping firm or a boat, what can we do?
Certainly, the plastic issue is just a huge concern. There's disposal of plastic in the open ocean, but a lot of it comes from land. It goes into the rivers, and that ultimately ends up in the ocean as well. So I asked you to take that pledge that I'm not going to use single-use plastic anymore. And it may seem small if you just do it, but if you multiply it by 8 billion people across this blue planet, it begins to make sense. And it's going to take time, but we're on the right direction. That's, as a scientist, you're always looking for trends, right? Nothing is really immediate. It's always, are you trending in the right direction? What can we do to change this trend towards the right direction? And I think the world coming together with plastic, and we'll be hearing a lot more from Mary this afternoon, so I invite you all to please stick around for that amazing talk. But plastics is one. Thanks, Pete.
That's at 2 p.m., by the way. Oh, it looks like Mary has a question too, Sid.
As I was saying, I'm a great believer in marine protected areas, and I have seen the dramatic changes they make in restoring the ocean. However, a real issue there that I know you're aware of is many of the marine protected areas aren't patrolled, so there's no way of knowing what really goes on in them. And that's a part of the system that countries or foundations need to find a way to patrol those areas to be sure they're really protected. And, I agree strongly with all the things you've said, except for the undersea mining, which I think is something we don't need to touch. I mean, we know that a tremendous amount of the life of the ocean is in the first foot or two at the bottom of the ocean, and we don't even understand that. And, as my great friend, and I'm sure Sylvia Earle always says, we shouldn't be destroying things before we even understand the systems. So I think any kind of undersea mining is opening a door that we don't need to open. And there's a lot of information put out saying that, we need this for clean energy and for batteries. And that's all inaccurate, because the battery industry and others have evolved to the point that they don't need those supplies. And it's really the parties that invested in mining that are trying to get mining to continue to get their own money out, and it's at the expense of our ocean and our planet. So I say no to undersea mining, and that's part of my message to the world too.
Thank you, Mary. It is the responsibility of the global ocean research community to monitor the environmental impact, if you will, of any deep sea mining. I agree with Mary, but the research community, such as JAMSTEC and other NOAA, it is our responsibility to monitor those impacts and produce the science about deep sea mining. And then, of course, others will make the ultimate decision. But we need to stand up and demonstrate the impacts of deep sea mining, in my opinion. Thanks.
Thank you. Coming back to Peterson's question, what is my individual contribution to this? I think the solutions we'll see in the next few slides. One solution is try to reduce the greenhouse gas. The other one is to keep us informed what is happening and make everybody aware of what is the situation now and how the situation will get better in the future by our contributions. And this kind of meeting is very helpful in that sense. Like when we talk to each other, try to spread a scientist point of view, and learn from the general public's point of view. Okay, this is what is happening, we're suffering because of that, and how science can help us, and what we will do together to improve our future. For example, we do many kind of projects. One of them is like predicting malaria outbreaks, predicting crop yield in some of the rain-fed regions where the farmers are completely dependent on rains. And that helps them to have a better mental state in very adverse situation, to avoid to have a better mental health. That's one of the things we talk for the younger generations. We see many news that school children are very distressed by what we are saying about the climate change because they don't know what will be the future for them. So we need to come together and make them aware, okay, this is what is happening, but this is not the end of everything. We have hope. As we can pick up seats on this slide, we have hope. The ocean is resilient. If we contribute individually by producing less plastic, by producing less detergent, by putting less detergent in the sea, and also like not using too much of air cooling so that we produce more greenhouse gases. That individually we can do. We can keep the temperature at 27 degrees instead of 22 degrees or 18 degrees. I see some of the offices 18 degrees in summertime. We are wasting a lot of energy and we are producing a lot of heat, carbon dioxide because of that. And that individually we can improve, I think, and also learn from each other's experience. That's the most important thing from us, I think. For us.
Thank you very much.
Please, you have a question. Thank you.
Yeah, thank you for the wonderful presentations and speech. I was just wondering, you mentioned ocean is being resilient and able to restore, and you also mentioned problems like Arctic ice melting and like rising sea levels. And it sounds like irreversible, but do you believe if humanity manages to stabilize climate change, like rising temperature or even make it drop, will it be able to restore naturally? Thank you.
I'll let our modeling expert answer it quickly, but so far, from what I understand, we've not reached the tipping point yet. There's still hope. If emissions are reduced, they can recover.
Yeah, I totally agree with Sidson that we are still in a state, if we behave ourselves better by reducing greenhouse gases, we will return back to the past. Having said that, we should not take all these things in a negative sense. There are two ways of handling this. One is mitigate by reducing the greenhouse gases. The other is to adapt. We know that this is happening. Instead of getting scared of that, let's adapt to the new norm. This is the new norm. We know that our models are predicting well now. We have more confidence on the model that those will predict the extreme events, the floods, the droughts. And based on that, we start making decision-making process. If this happens, this is our decision. We'll do this, we'll reduce the risk by doing this. And in that sense, we can tackle this problem in both ways, mitigate and adapt.
The data is essential for your work. How secure are the budgets to keep the data flowing?
I can answer that question. The program I helped start at NOAA 30 years ago for global ocean observations that I presented earlier, it's still standing. Yeah, doing well. It's a little bit repurposed, a little bit refocused, but that program is still standing and doing well. It's the only program in the world which has global scope. A lot of countries take ocean observations around their countries, but NOAA and U.S., this particular program is in the Indian Ocean, we're in the Atlantic Ocean, we're in the Pacific Ocean, taking in situ ocean observations. And the data are still flowing. So it's a great question, and there's good cause for hope. And other countries are continuing to deliver data as well. And we're all working together more efficiently. So if we have instruments and another country has ships, we're talking together more closely. So it's pulling us together in a more collaborative fashion to make sure the global ocean data are still flowing because they are so important. Thank you, Stephen.
Since there's been increasing utilization of AI technologies in modeling, I'm wondering if you're finding that earlier models are similar to current projections, if they look similar, and or if there are any that are dissimilar or what's the word, that you find especially interesting, this like new thinking or new directions?
Excellent question. I wish somebody had asked me this. Yeah, you rightly pointed out, so are the results consistent from what we have been doing for last 30, 40 years? The IPCC have this project called CMIP, Coupled Model Intercomparison Project. And we started with CMIP 1. Now we are at CMIP 6. And in these 20 years, 25 years, the models are developing. So we find the models projecting better until CMIP 4. From CMIP 4 to CMIP 6, I didn't see any changes in the model results. And it is both good news and bad news. Good news is that, okay, the models are consistent. Even though we are changing many parameters, many processes in the models are still producing similar results compared to previous models. But the issue is, even if the models are producing the same results, it means the physical processes we are trying to improve in the model are not working. We should have somewhat some different results compared to CMIP 4 or CMIP 5, especially in the rainfall and the temperature. We don't see any change, and that's not good news to us.
With a phenomenon like that, would you then, over time, with the rogue wave data, that would be, and so it can predict itself with the AI, or am I thinking correctly?
Excellent question again, and as you said, we don't have enough data at this moment of the rogue waves, only few of them now, last few years. And going forward, we'll have more of them, and the AI will learn from that. And in that way, we hope the prediction will be better in the future. Definitely, yes. Yes.
Okay, I think, did you want to say a couple of final thoughts, or are we all good to go, Dr. Thurston and Dr. Behera?
I would just like to say it's been a pleasure working with Behera-san again, and modeling is so important to what we're doing. And I want to give you all a sense of the role of science. You're hearing a lot of media comments, but I just wanted you to leave this amazing Blue Ocean Dome with the sense that there are thousands of scientists every single day measuring the ocean, they're modeling the ocean, they're looking for solutions for the ocean, and there are a lot of smart people, you know, that they're really, really smart. So I want to give you that sense of hope that it's within our hands. It's within our hands to have a sense of how this all ends. We can continue to, you know, do things that aren't helpful for the ocean, or you can contact your diet, your Congress, your parliaments, and enough is enough. You've had enough. You're not taking it anymore. The scientists know what's happening. We have solutions for it, and we need the policy to follow with their solutions. You're not helpless. You're not helpless. You're very powerful. And if you want a nice, clean ocean for your children and their children, you need to step up. You have a strong voice. You have a stronger voice than you think, and you need to make those comments. So hopefully today, what you've seen in the Blue Ocean Dome, you realize that there's a lot of good stuff happening, but we need your help. We definitely need your help to talk to your Congress and diet and make the policy decisions to use the science. So thank you very much for your attention today.
Thank you so much for coming. Dr. Behera, do you have a couple of few?
So, as I told before, that we have hope, and that hope comes from our understanding of what is happening now and what will happen in future by using the models. And the digital twin technology is developing very fast. It's a part of Challenge 8 of UN Ocean Decade, and it will continue until 2030, but there is a good possibility that legacy will continue even after 2030. So this gives us hope and stakeholder engagement, citizen science all together, and by providing information on very high resolution like 100 meter, 10 meter in coastal regions, we'll be able to provide solutions to many, many problems. And in future, we hope those things will be available on those kind of digital interface with AI in it, like fish tank, and also monitoring plastics, and we'll hear a lot about the plastic, how we recover them. But then we should monitor them and also project which are the regions where we'll have more plastic, whether we're reaching a tipping point for the plastic, because most of the plastics are degrading into nanoplastics. And once they are in nano form, they can easily enter our body, human bodies. So that's why it's a big concern for us, and we continue to monitor and project which are the regions we should be taking care of. And eventually we'll have these kind of coral models or the lagoon models, which will provide a kind of tool to everybody to create what-if scenarios. What if the pH level goes down? What if the temperature goes up? What happens if nitrogen is less? What happens if the iron is less? What will happen to those coral reefs? And how we can restore them to the normal state by changing some of those parameters. That's our hope. And with this hope, I think we should conclude our seaside chat, ocean side chat. Thank you.
All right, thank you so much, Dr. Thurston, Dr. Behera.
It's a pleasure. Thank you. Thank you.
And thank you so much for coming today. And just so you know, we'll begin our afternoon sessions at 1 p.m. If you're interested, I'll be speaking at 1 p.m. and then Mary Crowley, who's up there, will be speaking at 2 p.m. And then at 2:30 p.m., Soraya's son and Mary will be speaking together about an Oceanside Chat. So please join us. Thank you very much for being here.